Welcome everyone for High Performance Computing, Advanced Scientific Computing. This is practical lecture 4.1 and the second part about MPI communicators and data structures, whereby in the first part we talked really about the MPI communicators. We started actually with something called non-blocking communication, had a simple example on it to understand the send receive. So really not waiting for the messages to be delivered or to be received, but rather continuous application logic, which is sort of the idea with a non-blocking communication. But we also had then examples where we have this wait command, where we really have to synchronize then to get the application logic again in line between all the different parallel tasks. And we continued with a Cartesian example, nicely connecting to what we had also in lecture 4. Admittedly, lecture 4 was a bit dry, a bit theoretically, so we tried here now in this part 1 to have a little bit of practical example on this Cartesian communicator, which then adds to insight, I think, on a much more easier way. And we started with a Cartesian communicator with 3 times 4, a dimension 12 cores or 12 tasks to work on. And we have seen that this Cartesian communicator that we're going to create as MPI ComWorld is then nicely to use as, of course, the original MPI ComWorld communicator, but then we had 2 in parallel, and we could use this, obtain rank information, and also get then, of course, information if I want to do a shift between, let's say, different parts of the Cartesian. We get the information, what is my source and what is my destination, if I really want to send and receive information. So shift in a way is just preparing the communication to understand where we can do our messages or how we actually deliver those messages, while then the MPI send receive was still used really to deliver really the messages. And we continued in a 4x4 grid then with a Cartesian 2D, where we actually exchange information with all my 4 neighbors. And this is, of course, something which is related to real applications, because often, as I told you also in previous lectures, with the so-called stencil methods or any type of real application that want to have a domain simulated, exchanging information is crucial. And often the neighbor information affects what you want to compute in the next time step. So hence, this for loop that we created in the first part of really using the Cartesian with all the neighbors up, left, right, and down was quite essential to then compute the next time step. That's what we didn't do, and the final project will allude a little bit to this if you decide to use a phishing simulation. Hence, you would start with the overall loop of simulating the time step. So what we had in part 1 was just one time step, so to speak, exchange neighbor information, execute the program, of course, 16 times with all the different ones so it had. And we learned a bit about the periodic behavior of this Cartesian communicator. While part 1 was really, again, focusing on communication, and then also we thought about a little bit the idea of application logic that is following then, so physical formulas or so as an example, the computation, we here now in the second part want to look a little bit again on the data. So lecture 4 already in the second part discussed a little bit about parallel I/O. Discussed a little bit about more advanced, let's say, libraries like NetCDF or HDF, which is quite often used in communities. And we will look in this in a bit more practical detail. So I will demonstrate a little bit why MPI-derived data types are needed, how they connect to the normal data types that you know, like integer and so on, and why that is useful. Here and there, however, I have to say, it relates a little bit to the C programming of pointers into memory spaces and so on. So those of you who are not really very well in C, don't worry. I will make the point, and it's really the only, let's say, hidden element that you really understand or need to understand here in terms of C programming, that you essentially point to a certain memory location with a pointer. And with this, you need different data types really to get them over the wire. But we will discuss this. Also, unfortunately, because we moved in this semester relatively spontaneously from Jytte to Elia, we had not yet the chance to install a certain data science application on our Elia system. So we have the slides still on Jytte. But this is not a problem. The demo you can see actually in the recording from last year if you want. In this year, we have to just use the slides for this part. We try our best to, however, install HDB scan. These are things out of my hands. I need the administrators to create the module and so on. And they are quite, busy as well. So we didn't make it in time for this lecture. But in the end, we more or less have everything on the slides, and I will go through this. So don't worry about this. And let's start a little bit with applications again and motivate again the need for it. So we had already the idea of ghost regions, halo regions, ghost cells, as we also call them, right? And if you can imagine again that we have an earth science application and you want to simulate some element, you could think about these two extremes. Maybe you would say, if you have this whole country simulated in just a couple of blocks here, you would have lots of work and lots of data for each of single block, and you would say it's maybe little parallelism. Hence, that would be not so good. And then on the other hand, you can say maybe if you do it too much, right, then it's too small. There's a communication overhead that needs to be done because, as we learned with the Cartesian world, we have different processes here and you cannot reach the memory. So you would have to exchange memory, exchange physical informations. Let it be, let's say, different physical variables that you want to communicate to the other elements of it. And this could be meaning that you don't have just an integer, that you don't have just, one specific or couple of values, but you would need data structures which represent multidimensional arrays that have a very specific type of different, let's say, physical variables that you always want to do together. And we call that then a bit like a bulk swapping. You could, of course, now think about that in each of the iteration you do over time, you would, send, receive each of those, and every little integer, every little char, and so on. But of course, you can quickly come to the idea that this would extremely lead to communication overheads. Again and again, communication for these simple elements. Hence, these data structures that we use means that we have, let's say, not so many small messages, but a couple of messages that really have, let's say, substance, data structures which are bigger. And we come to this, what these data structures will be, just to motivate a little bit why these data structures exist, especially also in the light of your domain decomposition again that we learned in lecture 3. And then, of course, also, as we said before, we need this sort of ghost and halo region replications region around it. That what you know already, we have discussed this, so that these are basically not really existing. It's just that the next time step needs this information to compute some certain values in this ghost cells. Hence, you would use that before every time step is ended. You do a bulk swapping of the physical variable so that in the next time step, we would have everything we need for the computing in this particular cell, right? Or in this particular domain part. Hence, what we learned today is a bit related to domain decomposition again, and the need for data structures that we then also use in this halo regions bulk transfers. And how that looks like is best explained if we start at what you already know. And these are the primitive data types, sometimes also called intrinsic data types, right? So this is known, and whatever programming language you're in, you basically have a understanding already of integers, you have understanding of chars, floats, MPI doubles, and so on. And we have them here in the MPI environment also available as these primitive data types, also to enable code portability. So with this, we quite know what's inside these particular data type. We can use basically this in MPI send and MPI receive. You know that already from our previous lectures. So here again, just for you to understand that we always had put an MPI data type in, if you remember, right? Even if you have 3 integers over the wire, we put 3 MPI ins. And this shows the MPI environment, okay, there's an MPI coming, an MPI integer coming in this and this length. Now, you can imagine that when we have these earth science applications we just talked about, or any other more physical, maybe realistic simulation, we had the train that is burning, for instance, that we maybe want to have as a domain, and then chunk this down into different elements where, let's say, for instance, each of the seats will be a very specific part in parallel computed. We need to exchange lots of information, the heat in the train. We have to have the material information, the degradation or the burning status, maybe on all these parts of the materials, the floor, the ceiling, and so on. So there are different elements where you have to exchange lots of information, and then doing this all with a, let's say, simple data type means we have to do send, receive hell a lot. Hence, what usually scientists doing is they work with multidimensional data sets. They have arrays, matrices of sorts, where lots of data is in, and you would rather want to actually transfer those over the wire than having, let's say, send and receive done many times. Now, the trouble with this is, and this is a little bit alluding now to the C point in it and to the idea of point-to-memory parts. We had this already in lecture 2, if you remember, about MPI, how send and receive really works is it points to a certain buffer. And this is a buffer in memory where this information is there that you want to send. Equally, on the other end, you need place, right, to receive this particular data type. Hence, we also had in the MPI receive this buffer in order to write things into this buffer, and from there you basically put it in your own memory parts or whatever you want to do with it. But the key message to take away is really that this part is now something we have to work on significantly when we want to have now more advanced data types, because pointing in memory to a simple integer is easy. Pointing to one part of an array, if you have a multidimensional array and you put one part out, let it be a char, that's easy. But what happens if I want to transfer, let's say, a vector out of a matrix? This is something which is not obvious because the vector information that is maybe in the overall matrix is not consecutive in memory, right? Or contiguous in memory, as we would also here and there refer to this. And there are a couple of ways how you can create so-called MPI derived data types in order to make that happen. And these are the modus operandi how you would usually do it. You have essentially a new data type to create. And this is something coming out of your already existing MPI data type. So you can have collections of MPI ins, chars, or as we will see, we construct this new data type based on a certain offset in a vector, taking elements out of a matrix. We have even indexes we can use. So there are a couple of routines that can really create a nice data type from existing data. And then we commit this new data type to this environment of MPI. That's also important so that MPI knows this is a data type that everybody understands in the parallel, let's say, environment, right? So that's also an important part. And then the benefit really is you can just use this new derived data type and you don't have to do it in many send and receive operations, even if it is, let's say, a bit more complex. Let's say the vector out of the matrix. Let it be 3 integers in this vector. You don't have to do 3 times send and receive for this different, let's say, vector elements of integer, these 3 ones. You just want to send the vector. And that's what you do. You have committed it before. It is 3 values, and that's how you created it. So hence, we will talk about this. And it really helps us, again, the advantage in it to avoid all of these repeated send and receive operation, which makes the whole application really slow and potentially even error prone. Hence, this makes sense, of course, if you use it often, right? So if you have just one message exchange, maybe with a couple of integers at the beginning, for instance, of an application, then of course you have to balance the need of creating really a derived data type for it. But usually it makes sense to create them. And there are a couple of these construction routines, how you create a new derived data type. A couple of them I will demonstrate here. You see here contiguous, vector, and index, for instance, but there are more of them in the MPI specification. And they kind of always, address a little bit how we go with a more complex data type. The simplest you can imagine is the so-called string, which is not a problem in Java. I know many of you learn Java here. You would say a string with 3 chars, for instance. This is something already which is not so obvious. in the sending of MPI. Now it's very trivial in a way, you think, for us, because in a way it's just, you know, 3 chars next to each other. But this needs to be prepared in memory, as we know, so that we have 3 chars, and we could do it in the way that I say send and receive MPI char 1, MPI char 1, MPI char 1, and would always, you know, have 3 times maybe 1 char over the wire. But what happens if you want to really send it as a string with 3 chars together? And for this, there are different operations that I also want to demonstrate. And because it's a practical lecture, let's go immediately also a little bit on our Elia system. So I'm already here logged in, luckily, on our system. Let me just go here to prove it to you. We're on the login of Elia. I am Morris. So a couple of commands that you know. We go in our HPC course in the MPI directory, and we'll find now a nice example suite of derived data types. I will start with the contiguous because it's the best to understand, right? So we go into the derived contiguous idea of an example, and we go into the source code just briefly. As the name suggests, here we want to send something which is contiguous in memory, and we start again with our MPI init here of the MPI environment and finalize the usual elements. And here we start now with the idea of an MPI data type called double int type. And this double int type should nothing else be than just 2 integers that, you know, basically should go over the wire. So this is encoded here in the MPI type contiguous. So we have 2 MPI ints from the normal basic primitive type that we now establish and create as a double int type. And when I then commit this double int type to the MPI environment, now every core, every task in this environment has this information and can work with it. And this is of course needed because we see here we have a typical role of a, you know, kind of 2 tasks, and this will actually be the example of all the derived data types here. Of course, in a real production setup of an application, you would say it's much more larger tasks involved. So here we just make again the typical MPI send receive simple example just to show you how this, you know, MPI types work, because this is the emphasis of the lecture today, not the overall programming and so on. Hence, we have different roles. It's another way of identifying now the ranks information, where you can make it a bit more readable if you want to, you know, understand the source code quicker. Sometimes this is done. We have still our rank information, and of course get this rank information from our MPI com world. And based on this, my rank information, I would have then in the enumeration here from row ranks, the sender and receiver. So 1 will be 0, 1 will be 1, and hence different application logic. So far, so good. For the sender, it's important to create our buffer for the send, right? That is ready to send. And we initialize this directly. We're saving 2 integers, as you see here, very arbitrarily set with 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. And then, of course, sending this over the wire. But the interesting thing now for us is, when we send this with the MPI send command, we don't use now 2 times an integer or something. We use this new buffer, which we just initialized. So the 2 integers, which are still integers, and we point to them, right, with this operation. But we don't say 2, and we don't say 2 ints will be transferred to the receiver. Instead, we just use one of this new beautiful double int type. Admittedly, trivial example, as you know, it is always to better understand the concepts behind now these things, particularly put in focus on. But this makes it easier to say this is automatically 2 integers for the receiver in the MPI com world. Hence, we have our other role. In the receiver case, we have here, of course, our received array, that the buffer, so to speak, we still need to do also for the received. But instead of saying there is basically 2 MPI ints from the center to be expected, we have this one new beautiful double int type that comes to it. And then we get some status information and so on. and would get some values out of it, like the my rank, how much was really received, or in other words, do we have now this 1, 2, 3, 4, 5, and 6, 7, 8, 9, 0. We initialize this only in the sender, so if the receiver would not get this information over the wire, you can understand that this array is uninitialized, so it would have very strange numbers in it. So we assume when it will work with this application logic, we should have a beautiful output of received values in that type. So this is the C program. And in the slides, I skip now from now on also more and more the compilation, because it's getting a bit boring for many of you. It's clear that we have the same environment. So hence, I will demonstrate it here, how it works, that you can get the module environment and so on. Let's search in the history. You see it here. Remember, you have to have the right module history, and then we can do MPI CC and derived contiguous minus O derived contiguous. There will be again some warnings and so on, so don't worry about this. And we have still the executable here, which means we can use it and actually then also work with it in the job script. So let's have a view in the job script where we see then we want to execute this derived contiguous with 2 tasks per node. And this is what we will do with the spatch command that you also already know from many times and all of that. Hence, we also skip the S control and show job ID nowadays to put an emphasis more here now what's happening. By now, the job would be already completed. And when we now look into it, we assume the simple message exchange now and the outputs, where we say that the process 0 sends really these values over the wire. And because this was initialized, it's not the biggest surprise, but we can see definitively that it was received because we have a proper initialization, so to speak, through the sending of the array. In other words, this continues 2 MPI ints that we sort of not really needed here, because we created a data type which was now this funny double int, have actually worked because they were contiguous in memory. So this is also, of course, in the slides. So again, I skip in the slides more a couple of things like the compilation and so on, the loading of the modules. I also don't need to demonstrate this again and again. It remains essentially the same modus operandi all the time. Here, the emphasis is now in the output for this contiguous memory parts that we initialized here with this nice buffer. We have then also the output documented that this was received because this was never initialized, and also only the sender initialized essentially this buffer to be sent. We can see that it really worked. Now, what's the situation when we don't have something contiguous in memory? Hence, we have a vector example I want to show you next. The idea is in this vector example, pretty simple. We'll have a full matrix or full array if you want with 0, 1, 2, 3, 4, 5, 6, 7, 8. So 9 entries. And we want to extract and send, let's say, out of our scientific application, just the vector in the middle, right? So that means for us, we have some certain distance in the memory outfit here. Hence, we need here this count, block length, and stride to define in order to pick this 1, 4, 7. And when we commit this, essentially, here's an example of 5, 2, 3, you see that automatically the stride will be used when we use this particular type vector on this data type. So let's go and see this a little bit how it works in practice before we stand up with too much theory here. We have the derived vector example here now that we will look in. Again, I will skip now the compilation. You have seen that already, just that you see the source code is the same here that we have also on the slide. Again, for us now, it's important to have an emphasis on the MPI data type we create. Now it's called column or vector. Doesn't really matter. Let's call it column type. It is an MPI type vector that we have now defined as an MPI integer, where we have now this 3, 1, 3, and this is now the count. So we want to have 3 items, yes. Of each of them is, of course, 1 integer, but with a stride of 3, right? Because I 1, 2, 3 until the next, 1, 2, 3 until the next. Or in other words, you see that here, for the blocks to be really sent. Hence, this is the pointer we're going to create with this particular rule of this data type to send this information out and not the complete array or so. Hence, this is reflected mostly in the idea of here in descending. But let's start again with a buffer that we have 3 times 3, as we had also on the slides. And then we would send information out. You see here the pointer of the buffer is just at 0.1. Hence, we don't really send this, what you see in the printf. Instead, we put a pointer to this buffer location, which is then really the first idea how the column type will start using these offset information to the receiver in the MPI Com world, so no surprises there. What we expect is, of course, having 3 received, right? And here we do the example of saying, instead of using, again, the column type, we can also play around and say we receive 3 MPI ins, because we know that the column type is like that. And we will see, hopefully, that we really received 3 integers. Of course, again, this is a toy example. In bigger applications, you would maybe have much bigger setups where this is not at all so simple. So let's actually go out here and think about executing this as batch. Now maybe we go quickly in the job script here. Also here you see 2 tasks. We have the derived vector that we execute on U2 on our partition. So let's do this as batch submit derived vector. Also, this will be very quick, so the output is immediately there, as you see here already. This is already finalized. We have the output here, and if we more it, we should see now the 3 integers that have been really sent over the wire. So here we send the interesting new column type 147, and here we receive the values as 3 MPI ins because we know the column type was like this as a check. Showing you specifically, I think, in the area of MPI send that we use this buffer location 0.1 to indicate the first array part. But from that, we don't basically define as we have it in the printout here. Rather, we use this 1 column type, which then gives us the information. And you see also it's much more beautiful in code instead of doing now buffer 0.1, 1.1, 2.1, and so on to send. Also here we see again the example that the array that we have here, the integers, the 3 in the received, is not initialized, right? So we would have very strange values if it wouldn't work. But we exactly got 1, 4, and 7 over the wire, and that's also in the outcome. So that's nice, and let's see again, the vector was probably pretty straightforward and in fact often used in scientific applications, but there could be one more complex aspect that I also want to demonstrate a little bit with this indexed data type. Hence, the next demonstration would be perhaps a bit more complex, but what sometimes applications are interested are, let's say, having just one part of the matrix, a diagonal, or elements like, say, what we see here as the example, where you have the full array like this. Again, our array we had before, but we don't want to send now a column, but we send a certain rule. For simplicity, we put here the rule, in every different row, we want to have one more value, but this is of course something now which you can play around with. And you see a little bit how that works on this beautiful example here, that we want to extract first 0 and block with 1 element, but then you also in size are able to steer the block length. Hence, we have a block length here that you can work with, and then also the different indices. So where you want to basically extract information for these 2 blocks in order to get this. Again, let's have a practical lecture. So let's move into the practice here, how that works. So we'll be leaving the vector application and going into the derived index one. What would be the last one? Again, just to see that the source code is there, you see that, and I have compiled it already, so not waste time again and again show you the same things. But when you go here in the idea of the data type, we do a triangle now of this matrix. We have a certain displacement. We have this length that we gonna create. We create an MPI index now based on this 3 lengths and the displacement, which are then, so to speak, the indexes. And we see that the length is first 1, then 2, then 3. Let's relate this a little bit to our graphic here to understand this. So the length is 1, then 2, then 3, right? So this is what we see here, 1, 2, and 3. But we also see the displacement. So first 0, then, so 1 at 0, and then we had 3 here. So 0, 1, 2, 3. That is our next, where we are, basically, the next displacement. But in this next displacement, so to speak, we want a length of 2. And then in the third displacement, which is 6, we want a length of 3. So this is what we command here, right, in these indexes. And this should be getting over the wire is kind of 3 different elements. And as MPI integer, which is the original one because it's the values in it, but still the count shows us at this position we will transport these 2 integers and we transport the 3 integers, not just one MPI int. And with this, we have a triangle type created out of the overall buffer matrix that we have here, that we also give out a little bit here, just for the purpose of showing you what would be really in it. And what we, however, do is in this buffer here that we initialized, we don't really go in all these complicated detail that we just discussed and create, that we can now reuse and reuse again because it's committed as a triangle type. We just point to the buffer, basically our matrix, and say one triangle type. And all of these rules with the displacement and the length of the different blocks and so on that you see a little bit here now go over the wire, pointing to the first buffer element to the receiver. Hence, what we should get is 1, 2, 3, 4, 5, 6 values of type MPI int, no surprise. So we test this a little bit in our received. Now we're changing this to 6 MPI ints that we should get from the sender and give them out here. This is not initialized, so again, it would be strange values, but we want to obtain really our values that you see here on the slide. So let's see if that really works in our practical lecture part here on Elia, where we now have a job script also, of course, derived indexed, and then we can see we execute this here with 2 on Utun, partition as budget. Again, these are simple jobs, almost immediately ready. So showing more the power of MPI with different elements. And we see here that MPI process 0 sends the values 0, 3, 4, 6, 7, 8. And what we really see then also to compare with this is we really receive these values 0, 3, 4. By just sending a triangle, we're receiving 6 of these MPI ints. Again, these values would be very strange values because it would be uninitialized arrays. But now the receive was really working, overwriting, or basically properly setting the index elements. Hence, simple examples, and I think the graphics in combination, of course, and with the specification show you quite clearly how you can work with this, also with more, let's say, interesting setups on the whole matrix. But I want to end the application of this data types and structures a little bit also with some other element. And this is related more to something we already know from Parallel with HDF5. So we're leaving essentially the direct MPI type world now and would go to something a bit more, let's say, bigger and bolder and often used. Again, we always demonstrated this a couple of years now, but it's unfortunately not yet an Elia, so I can't do it in demo, but everything which you really need to understand is here on the slides. So firstly, you see here some interesting job script. Again, this is on the Utun system, but it doesn't matter. We have the executable db scan that we get out, and we can have Bremen data here, is different data sets, but they are in HDF5 format. Hence, there's a clustering algorithm, HPDB-scan, that based on point cloud information would reconstruct the inner city of Bremen. So that's an application typically there. And you see different data sets, so they have different sizes. So this is the idea of this. You see that a little bit in this application, how it works here. There's a car driving through the city of Bremen, shooting, out and with a reflection getting a point cloud back. But the point cloud is not at all a city, right? It's a loosely connected form of, points in space. So hence our clustering algorithm, based on this Bremen data, is reconstructing this building based on, neighborhood, on Euclidean distance, and so on. And this is what you see here. Dataset 1, dataset 2 are the different datasets we used. You see that's an MPI application. We already discussed it in one of the lectures, also because of these different domain decompositions. But this is an example now where the data, and that should be now the focus, the point cloud locational data, so where they basically are in space, is encoded in this HDF5 element, right? Hence, our application needs to read all of these point cloud parts, which is not yet a city, into the application. And it does so with Parallel I/O and HDF5 in parallel, so that every one of these different cores that we are using here in this diagram has this information accessible via this binary file format HDF5. And then it performs a clustering on it, right? Given the rules that we implemented, we see overlay of the grid and then estimate splits, as we discussed here, and then merge halos, local DB scans, and then go with ghost layers and so on. I think it would take a whole lecture just to explain HDB scan in details. Of course, there are papers around it, and you see we actually use this also for other applications. Here we're counting flies that are intoxicated and lying on the bottom of some element to be counted. So you can use it in different application examples, but the point is we use here for this data structures now the hierarchical data format, which essentially here is in two versions, the Bremen big one and the Bremen small data set available as H5 files, you would say. And HDF5 is now relating to one of this high-level I/O library I was alluding to in the last lecture, lecture 4, where we talked about MPI/O in general, but often people use them, these libraries on top. Hence, also one part of your assignment was to think about when we include HDF5, what we have to change from the module setup, right? So internally, the hierarchical data format, as the name suggests, is almost like a file system in itself. You have something like slash orientation, where you can have then images, 3D arrays, different parts of the data. You define it how to do it. And that's what we have done actually when we did our way of creating a data structure for this clustering. Hence, if you look into this now, as I told you before, it's pretty bad because it's a binary file. So with more Bremen small that you already know from our outputs of the jobs, we cannot come far. It's a binary file format, hence not readable for us. So there needs to be specific readers that actually look into this H5 files. And here's one example of the H5 dump that you can use, and that when we use it with Bremen small, can show you the clusters and the colors. And from this information, we basically get from that now something where we have the location of the data. And while the clustering is happening, we write then after the clustering back exactly in the same file, right? That these particular points are belonging to which particular cluster. Hence, when you want to use with it, you need a local copy because we do reading of the initial setup of all the point clouds. But of course, we also write then the colors back that you see here, which in the respect of the buildings show now the different buildings, hence our output of the job. And this is in the same file. Hence, we read from it, but we also write into it back the result. And this is something which is quite common in this domain of using Parallel I/O. And you have to make sure that you then take your copies of the data. Usually be careful with this, once you have a clustered data set. Of course, the unclustered data set will be overwritten, and then you don't have an unclustered anymore. There are obviously different parameters where the clustering can change. You see the neighborhood, the epsilon neighborhood, and another rule that constitutes how many points you actually think about constituting clusters and so on. And it's a very nice algorithm where we in the research group have one of the most scaling algorithms, thanks to one of my PhDs in the past. It's still out there, still open source. You see a little bit how that works when we now use again the HDF5 dump. When we go into the clusters, you see Bremen small, essentially before we clustered the point cloud with lots of zeros inside, so no assignment to specific clusters yet. And then we can run it with the job script I just described. Obviously, we have to also module load HDF5, hence what I said to you also in the assignment space, right, is one part of the assignment. Make sure that you have that firstly, of course, somewhere probably in the C program, but you need it also again as modules when you want to have a job script around it. Again, don't use this job script on Elia. As I said to you, it's a job script we had on Uton, unfortunately, on the Uton HPC system. Hence, we will work on it to port it to Elia at some point in time. And when you then execute it, you will see firstly the local DB scan helping, and then after this local scan and having, basically redistributed and everything and sorting the points, and the local scan is happening, merging neighbors is of course then also something where you can think about. Now it's happening that I asking my neighbors, do you have a cluster in the close proximity of a, let's say, Halo cell in a way? Then we probably want to merge the clusters depending on the rules again and so on. So there's a certain merging taking place so that you have the whole domain covered. Now more on the data side, which is now the important part here. If you don't understand completely DB-scan, it's not an issue here. The more important part is to understand that HDF5 could be now used to assign different clusters. You see here that the data structure we use for clusters in Bremen is first 0, not assigned, and when you run it, afterwards you have certain cluster IDs, or some of them would be also saying they belong to no cluster, this minus values, but some will say it's this particular cluster with 4825. Hence, this is a way to also work with data. It's a standard way of working with data, HDF5. Also NetCDF is often used. And that's really, I think, all I leave you on the table for today. Obviously, there are whole seminars around HDF5 and MPI, as I told you, from 1 week. That is, of course, something we could have the whole course about, but that is not the idea of this particular course. We will continue with a little bit of an interesting application scenario around OpenFoam and then also Rescale before we then also come to shared memory programming in lecture 5. So talk to you next time.